Okay, now in this question we're being asked how dilution affects effectively strong and weak acids. Two of the acids are weak acids and one acid is a strong acid. And this, obviously the pH is going to go up because the hydrogen ion concentration will go down in all three cases. But because effectively we're dealing with one equation, the strong one, which is not in equilibrium, is that going to be the same as a weak acid, which is in equilibrium? That's really what this question is about. Now obviously in a strong acid it goes to completion on the other side. We start, whatever we start with ends up basically finishing off completely as products on the other side. So if we have 0.1 mole per litre HA, it becomes 0.1 mole per litre in hydrogen ion concentration with the nitric acid. And if it was changed to 0.01, it was 10 times less, so it would become 0.01, and then it's obviously a pH of 1, and this is going to be a pH of 2. So for a strong acid, it's a very straightforward explanation. The weak acid parts are a little bit more involved. Now, weak acid is different. This is an equilibrium. So when we make a change, it may respond to that change to re-establish the ratio or the Ka, and so we have to have some understanding of how that works. Now if we just look at this for a second, I know it asks says no to calculations, but just looking at the actual expression here and put some values in there. So for instance, if we say we have a 0.01 concentration of acid, now that's not a terribly weak acid, that would be kind of relatively strong in fact, but if we just use that for a second, just for the sake of this, just some made up values. And if we had a concentration of the acid as being 1 mole per litre, so that's just terrible writing there, just a minute. So if that's 1 mole per litre there, and if we actually did that calculation, we'd have a Ka of 1 times 10 to the negative 4. Now Kas must stay constant because they are a constant. Now if we just assume that we changed everything by a factor of 10 in terms of the concentration, that would mean that this would obviously become 0.1 and this would become 0.01. Now this is a squared value, okay, I should put that in earlier, but there you go. Now if we just recalculate this with those new values in there, we wouldn't get 1 times 10 to the negative 4 anymore, we'd get 1 times 10 to the negative 5. Now that means the Ka value is obviously decreased, and the constant cannot change. So that means that immediately what this tells us is that we can't just change things by a factor of 10 when we have a power involved. When this top, if the numerator and denominator were exactly the same and we change them both by a factor of 10, then yes, what the Ka value would stay the same, but because the numerator is squared, that doesn't happen. Now the only way to get this back to this constant is by increasing the value of this and or decreasing the value of this. Now naturally, because we're not just talking about numbers, we are talking about an equation, what that does tell us is that if we increase the products, we naturally automatically will decrease the reactants. Now obviously we're talking about the weak acid concentration would get lower and the hydronium ions would increase. And what that really is telling us is that the equilibrium would shift over to the right. Okay, so it gives us some understanding of how it responds to the change by decreasing the concentration. Now just to get this straight in your head, realize what we're talking about is we're still diluting this by a factor of 10. So if we went from 1 mole per litre to 0.1, it would respond to this change by decreasing it even further to say, whatever value, but a value less than 0.1. This H3O plus concentration obviously has gone down, but because the equilibrium has shifted over to the right, it won't go down as much. So it will increase, but it's still going to be a lot less than it was. Okay, so instead of going down by a factor of 10, for instance, it may only go down by a factor of 9. Now, to work this out, you'd need some actual values to put into a Ka expression, and it would take a little bit of trial and error to actually work that out, but it could be done. And so from that we can infer that with a weak acid, the actual weak acid itself will decrease by more than a factor of 10, and the hydronium ion concentration will decrease, but not as much. So the equilibrium will shift to the right, and it may decrease by a factor of something less than 10, whatever that may be, by a factor of 8 or 9 or 7, we don't know. Okay, so if you can make some kind of explanation with this, and this is not an intuitive question in terms of answering it, but if you realized at the start that there may be a difference between a strong acid which completely dissociates and one where there is an equilibrium, and when we look at the weak acid we know that the numerator is squared, so it's not a linear relationship, that it's not going to be exactly the same. That would have given us a better understanding of it. Anyway, that's one of those questions you have to do your best to explain that second part. And I probably, even though it says no calculations, I probably would have put something in there and then talked about how the weak acid would have dissociated more, and how the hydronium ion, that would have meant that there was more of it, and that would have then, because of the Ka expression that we're talking about here, the weak acid expression, which is really what I'm talking about, that's squared. That means that it isn't a linear relationship, therefore we're going to get an increase in the H3O plus in response and a decrease in the HA, and that will keep the Ka constant. I'd have talked about that. Okay, and that's that question eventually answered.